And thank you for the opportunity to speak in this great opera house. I've had a sore throat all week, unfortunately, though, so I will resist the opportunity to sing my talk. So broadly, I'm talking about responsive parallel programs. And to give an introduction to what I mean by responsive parallel programs and why I think you should care, I want to start by talking about a responsive program that you all probably use every day. Some of you are probably using it right now. And then talk about parallelizing it. So the responsive program I'm talking about is an email client. And why would we want to parallelize an email client? Well, I recently realized that I was coming into my own as an academic when my inbox started looking like this. To add insult to injury, now every time I open my email client, I get asked if I want to compact the local folders to save disk space, because my email is just taking up too much space. So, okay, why not? Sounds good. This is a bit of an exaggeration, but surely you've all started a computation that takes way longer than you think it should to finish. And so what can I do about this? Well, my laptop is on the cutting edge of 2012, and it has 4 processors. Newer, fancier computers have even more processors. And so maybe we can leverage some of that parallel hardware to make this computation go faster. So we're in luck. There are actually a whole slew of languages called implicitly parallel or competitively parallel languages that are designed to take a big computation and make it go faster by using multiple processors. So the nice features of these languages are that they have high-level parallelism abstractions. Good, we're at ICFP, we like high-level abstractions. Threads are very lightweight. So you can take an embarrassingly parallel computation, like compacting 10,000 or 10 million emails, and assign each one to a thread, and the language runtime takes care of actually figuring out how many of those threads to run on different processors, and how much of this parallelism you can actually exploit. And finally, we have very elegant cost models, which you can use to provably reason about the amount of time that a program will take to run on some number of processors. And so these are nice features for using these kinds of languages. So if we use one of these kinds of languages to try and parallelize our email client, okay, great, so now it runs maybe 4 times faster. But of course, compacting emails isn't the only purpose of an email client. I might want to try and sort my emails. I might want to press some other button to do something, send an email, something like that. And if I do that, well, if I were using a Mac at least, I would see this. So why would that happen? Well, the problem is that there is one thread, or maybe a small number of threads, for handling the event loop of the email client. Incidentally, I noticed on the Strange Loop Slack yesterday that talks about fiber arts get a much bigger audience, so I'm hoping I can fool some people by including the picture of sewing thread here. So there's one thread to handle the event loop, another thread to handle compacting the emails in the background. Of course, we just said that we're trying to parallelize that, so it's actually not just one thread compacting emails, it's many, many threads compacting emails. And so the runtime of these cooperative languages isn't able to distinguish between the one thread that's running the event loop and the thousands or millions of threads that are compacting emails. And so the result of that is that your event loop gets run whenever the scheduler happens to get around to it, which is not the best thing for responsiveness. So the goal of this talk, which is cut off at the top there, is to take these models and cooperatively threaded languages and add priorities assignments to threads. So why is this hard? Why can't we just take any standard approach to prioritizing threads and add it to our favorite cooperative language? Well, these standard approaches have a couple of problems. First, most current approaches to prioritizing threads draw priorities from a fixed, totally ordered set, which is inherently antimodular for reasons that I'll talk about in a minute. And the other is the classic problem of priority inversions, which I'll also discuss. So to talk about why current approaches to priorities are antimodular, let's say that we're writing our email client and we have a system with 3 priorities, 0, 1, and 2. So we write our program, our thread to compact emails in the background at priority 0. We put our event loop at priority 1. And now maybe that was poor planning because now we want to implement another thread to send email. Well, that should be higher priority than compacting the emails in the background, but we don't want it to delay the execution of the event loop. So we have to go back and rewrite all of the code for the event loop to make that at priority 2. We can send our email at priority 1. We had to do a lot of work to do that, but okay, things are all right for now. Until we want to implement another thread to display a security alert, which should be higher priority than the event loop. Well, now we're out of luck. Fortunately, most systems for thread priorities have more than 3 priorities. In fact, even decades ago, the Mesa system had 7 priorities. So we're okay for now for our email client. But of course, you can imagine another program which would want to do 8 different things at 8 different priorities, and then you'd be in trouble. You can probably see where this is going. So could the implementers of pthreads on Linux. They gave it 100 priorities. So now with 100 priorities, we're trying to implement our event loop, and should it be priority 40 or 45 or 42? At this point, I don't even know what these priorities mean, and neither do most developers. So instead, in our system, we use an approach that has been suggested over the years by a number of different authors, and we use a user-defined partial order of priorities. This still leaves us with the problem of priority inversions. So what's a priority inversion? Well, let's say you have 2 threads, a low priority thread and a high priority thread. The low priority thread takes a lock that the high priority thread needs. And so now you have a high priority thread depending on a low priority thread, which may be okay for now, but let's say that you have a medium priority thread that's preventing the low priority thread from running, and thus preventing the high priority thread from getting the lock and running. This may seem like a contrived example, but actually it was almost exactly this that caused NASA several days and probably millions of dollars of pain and suffering back in 1997 when they launched the Mars Pathfinder mission. So this is a real problem, and in our system we have a type system to statically prevent priority inversions. So without further ado, the contributions of this paper are a language which we've called Primal, which draws priorities for threads from a partially ordered user-defined set, and has a type system to statically prevent priority inversions. The thing that I'll talk about for most of this talk, actually, is the cost models, how we take existing cost models for reasoning about the throughput or the total computation time of parallel programs, and how we extend those to reason not just about the throughput, but also about the responsiveness of responsive parallel programs. So Primal is a 2-layer language where the expression layer consists of pure expressions. It's an ML-style expression language, and these expressions do not depend on priority. They're totally independent of priority. They can run at any priority. The other layer is a priority annotated command layer. So commands are the things that actually interact with threads, and those, because they can sync and spawn threads, have particular priorities that they run at. So we have a couple of additional types on top of the normal types of standard ML. We have a type of encapsulated commands, which are annotated both with the type that they return and the priority that they run at. Same thing, threads are first class. There's a type of threads annotated both with the type that the thread returns and the priority that it runs at. So here the type of the return value is tau, and the priority is rho. So we also have an additional expression on top of the normal expressions of ML, which is an encapsulated command, again annotated with the priority it runs at, and commands can evaluate expressions and return them as the result of the command. We also add declarations for actually declaring the user-defined set of priorities. So you can declare as few or as many priorities as are meaningful in your program. In this case, we have 2 priorities, alert and background. And you can also declare as few or as many of the orderings between them as are meaningful. Again, this is a partial order. So we can say that background is lower priority than alert, but if there were some other threads in our, other priorities in our system, we might not want to specify the ordering with those. So once we've declared priorities, we can spawn threads at those priorities. For example, we can spawn a thread at priority background to compact old emails. We can spawn a thread at priority alert to display some alert. Like I said, thread handles are first class, so spawn will return a handle to the running thread, which we can then use to synchronize with it, to wait for that thread to complete. So here's where we can actually create a priority inversion. If you are a high priority thread at, say, priority main, and you try to synchronize on a low priority thread at priority low, as this code does here, that is a priority inversion and should be ruled out by our system, and indeed it is. We'll get the type error that in order for this code to be correct, we would have to have the constraint that the priority main is less than or equal to low, and we've specified that that is not the case, so this constraint is violated. The paper fully formalizes the type system in a core calculus that captures the essence of Primal. So the important rule here is the one for sync, which I've displayed on the thread, on the slide. And the typing judgment for commands is annotated with both the return type tau and the priority row at which the command runs. So that allows us to specify constraints such as if you sync on a thread, the priority row that you're currently running at has got to be less than the priority row prime of the thread that you're synchronizing on. And so that's the rule that prevents priority inversions. So I've talked about the language and the type system, and I want to spend the rest of the time talking about how we extend the existing cost models to reason about not just throughput, but also the responsiveness of these responsive parallel programs. So the existing models for reasoning about the cost of parallel programs talk about parallel programs as DAGs, directed acyclic graphs, that represent the dependency structure and the opportunities for parallelism within a parallel program. So in these kinds of graphs, the vertices represent sequential pieces of computation, and the edges represent dependencies between them. So in your head, you should really be thinking of a vertex as a single unit time operation, possibly a single processor instruction. But of course, if I were to actually draw the graph that way, this last vertex would be probably back by the hotel. So I'm not going to do that. I've cheated a little bit on the slide and collapsed long chains of vertices into just single vertices. But again, just think of a vertex as a unit of time. The additions to the model that we have done in this paper are to explicitly represent threads. So the shaded boxes and the edges within them represent a thread, so a sequential sequence of operations. And the edges between the threads are spawns and sinks. So you should read this left to right. The starting operation of the program is this spawn at the beginning. It spawns another thread, and we go on from there. Threads in our model have explicit priorities, which we represent both by annotating the box with a name for the thread, A, B, C, D, and the priority that it runs at. And graphically, the high priority thread here is in a darker shaded box. So this DAG represents a program that computes the third Fibonacci number in parallel, and then at a higher priority does some interaction with the user. So for the traditional models, we can read off cost metrics from this graph that immediately allow us to get some bound on the amount of time that this will take to run on P processors. So the two cost metrics that are important here are the work, which is just the total number of vertices, the amount of work that needs to be done in total by the program, and the span, which is the length of the critical path, or the longest path in the DAG. So the bound, which is attributed to Brent, is that in the best case, every time unit, we are doing P units of work, which we can count against the work. In the worst case, well, no matter how many processors you have, you can never do better than the span, because that's the longest chain of things that has to be done sequentially. So this is the traditional bound for parallel programs that just do computation. But our program, our email client, our toy program on the previous slide, does more than just computation. So we don't just care about the total amount of time that the program takes to run, we also care about how quickly that high priority thread finishes and responds to the user. So it's no longer enough to just have any scheduling of the program. We actually need a particular scheduling, which we'll call a prompt schedule. So a prompt schedule keeps as many processors busy as possible. That's a reasonable thing to do, but also tries to do high priority work whenever it can. So let's say we have two processors, and we're trying to schedule this program. So at the beginning, because of the dependencies, we can only do one thing, but then that will spawn additional work. So now we can run these two vertices. And now at the third time step, we actually have a choice, because there are three vertices that are available to run. So we could do these two, or these two. But I said that we were trying to do high priority work whenever we can. So we'll definitely want to run the high priority thread, and then we can just choose arbitrarily between the other two vertices that are available to schedule right now. And then we'll continue on like that. So you'll notice that under this schedule, the high priority thread actually finishes quite quickly, and that's what I mean by responsiveness. So we can formally define this notion as the response time of a thread, which is how quickly that thread runs after it is introduced in the system. So more precisely, it's the number of time steps between when the thread is first spawned and right here, when the last vertex is scheduled. So that's the quantity that we want to minimize, in addition to just throughput. So there are two important cost metrics that will allow us to reason about that. The first is something like the work, but it's not just the work of the thread that we're interested in, it's also the work of any other threads that might be in competition with that, might exist in the system at the same time. So in this particular DAG, there's a whole lot of work that's in the system at the same time. So you would think that that competitor work would be huge. But because of the priorities, we're only actually interested in the competitor work that's at a higher priority or incomparable, not lower, than the thread that we're interested in. So in this case, the competitor work of that high priority thread is actually just the thread itself. The other property that we are interested in is something related to the span, which is the critical path of the high priority thread that we're interested in. The definition is a little bit more complex than that. See the paper for details, but for now, just the critical path of the thread that we're interested in will suffice. So let's say that we switch one of those low priority threads to high priority. So now the high priority thread C actually depends along its critical path on lower priority work, and this is actually a priority inversion. So there's no way, just using a prompt schedule, that we could efficiently schedule that program. So we have to actually rule out such DAGs. So we'll call a DAG well-formed if it doesn't have a priority inversion like this, and our scheduling theorems are quantified over well-formed graphs. But if you have a well-formed graph and P processors, we have a bound very much like the Brent bound from Brent's theorem that says that in the best case, you're making P units of progress against the competitor work, and in the worst case, you're at least making progress along the critical path. So we're able to bound the response time of a thread. So I've talked about programs in Primal, and I've talked about graphs, and so far I've given no way to link the two. So that's done using a cost semantics, which takes a program in Primal and produces not just the value to which it evaluates, but also a graph representing the dependency structure and the parallelism opportunities in that program. So now we can take a Primal program, use it to get a dependency graph, and then use the graph and those theorems on the previous slide to reason about the responsiveness and the throughput of that program, assuming that we can show that that graph is well-formed. But we can because of this theorem that's in the paper, which says that if a program is well-typed, the type system ensures that it has no priority inversions, which means that the graph that it produces in the cost semantics is well-formed, and so we can apply the scheduling theorems. For the sake of time, I've glossed over a whole lot. The main thing that I've glossed over is that I haven't shown you any proof that the amount of time the cost semantics says a program should take to run is actually the amount of time that it takes to run, say in the operational semantics. We do have a proof of that. See the paper for details. We also have a compiler that compiles Primal down to standard ML, a parallel version of standard ML. And we also have a number of example programs. So see the paper for details. Thank you very much.
So there were actually quite a few questions. Obviously cannot get through all of them. But starting first with a question, can the usual way to fix priority inversion, the low priority task will temporarily inherit its priority from the higher priority task, can that be included in the system instead of rejecting such programs as being ill-typed?
So the question is about something like priority inheritance. Could we encode something like that? At the moment, no. So that's one of the things on my wish list for the system, is being able to more generally just change the priorities of threads at runtime, which would allow you to do something like priority inheritance. At the moment, we don't have that because it enormously complicates being able to reason statically about not just, I mean, this would solve priority inversions, but we also want to statically be able to reason about the cost and the responsiveness and being able to dynamically change the priorities of threads. I'm not quite sure how we would do that, but certainly it's something I do want to think about. Okay,
another question from Jenny Hackett. Does ruling out priority inversion prevent you from writing certain useful programs? Can you always avoid high priority threads waiting on low priority ones? Kind of two questions.
So the slight cop-out answer is you can always write the program you want by just changing the priority annotations. So that's a cop-out because the priorities presumably have some semantic meaning to you. So the biggest use case where you might want to be able to express a program that you know is safe, but that has a priority inversion according to the type system, is say if you could prove that the priority inversion only occurs for a bounded amount of time. So there's some research on bounded priority inversions, which is, again, something that would be interesting to include in the system. And I think this would probably be something that's a little more tractable at this point, because we do have a way of reasoning about cost, about how long things in the program can take. And so it wouldn't be totally out of the question to start reasoning about, in this system, under certain constraints on how things are scheduled, how long could this high priority thread possibly be waiting on a lower priority thread? So that would also be something interesting to add to the system. But you're certainly able to express a lot of interesting programs, even with the fairly strong restrictions on priority inversions that we have now.
Okay, and one more question that's kind of shared by a few members of the audience. So Mikhail Meyer and Phil Wadler both asked a question about the Mars rover example. So Phil asks, you gave an example where the priority inversion affected the Mars rover, but what went wrong? How would your type system catch it? And how would you alter the program so it would type in your system?
So what went wrong in the Mars rover had to do with locks. And so since our thread doesn't, our language doesn't have locks, the easiest way to sort of draw an analog to that in our system would be a high priority thread syncing on that lower priority thread and waiting for it. So then the type system would be able to just point out that you have this high priority, say, watchdog thread that's waiting on the low priority weather monitoring thread. I forget exactly what the threads involved in the Mars rover example were, but something like that. And so the type system would show that this was the case. So then you would have to go back and look at your program and see, well, why did the watchdog thread depend on that lower priority thread? Is there some way that we can pull out the piece of that low priority thread that is actually useful or necessary for the high priority thread to run and elevate that statically to a higher priority? So it forces you to reason about your code a little bit more, but indeed that is the purpose of most type systems. So I view that as a feature and not a bug.
Alrighty, let's thank the speaker.
Thanks.